Welcome to session 21 in our series on electricity and magnetism. What you just saw were these three rings here interacting with a electromagnet fed by 120 volts 60 cycle AC. And let's take a look at it from the side. That interaction between the coil and these rings, that electromagnetic interaction is the fundamental interaction that allows us to have induction motors. Induction motors happen to be one of the most common motors in your home. You probably have more induction motors in your house than motors that have commutators. So let's start from the beginning, and we'll find out what moves these rings. Now, I'm going to place this coil of wire with Christmas lights over that steel core. Okay? So here's that coil, and I'm going to energize this and take a look at what happens to the lights. Notice that they're brighter at the bottom and dimmer up at the top. What do we have here? We have a primary, a secondary, and then we have a magnetic circuit that links the two. The magnetic field comes up through the steel core, but then returns to the bottom of the coil through the air. Now, I'm going to use a different coil this time. This is a coil without Christmas lights, and the ends of the coil are just soldered together, so it's a continuous loop for the electricity to travel in. Let's place it over the core here, and I'm going to activate the primary. And what we have is a secondary that's free to move. Now, this coil is mostly rubber or plastic. Most of this weight, or at least half of it, is probably the plastic. And the wire is pretty thin. So some of the weight here is just wasted. It's not useful for the motion that we're observing. Here's another coil made of magnet wire. In this case, most of the weight is now the copper wire versus maybe only half of the weight or 2/3 of the weight being copper wire. So this has a better power to weight ratio. Let's see how it behaves when we put it over the little core here. So let's put this on here, and you know it's going to go way past here. So I'm going to take us to a different view. All right, you ready? Here we go. Let's do that again. Here. Now, as we saw before, it doesn't have to be a coil of wire. As long as we have a continuous circuit, a good conductor, and a ring will do the same thing. That's how we started. So we're going to explore shooting this one up. Let's put that on here. And all right, let's see how we do. Whoops. And finally, it doesn't have to be round, just probably balanced is best. Put this on here and go back to that view. I might hit my camera. Actually, why don't we'll have you look right at it as it's coming up, okay? Here we go. Okay. What's causing that to rise? Well, let's take a look at this drawing right here. So here's the primary with alternating current being fed into it, producing a changing magnetic field. And that magnetic field will generate electrical currents in any kind of loop that's up here. In this case, it's we're showing a picture of the ring. So the changing magnetic field is producing electrical currents in the ring. Now, the magnetic field doesn't just go up like that. It goes up, but some of the field starts returning very early on back to the bottom of the primary coil. So we have a radial component all the way around coming out of the core here. But we have electrons that are moving perpendicular to the paper and a magnetic field that's going out that way or coming this way, depends on what part of the cycle it's in. And when we have electrons moving perpendicular to a magnetic field, the Lorentz force tells us that we have a force that's perpendicular to those two vectors. Now, if you were to do a thorough analysis, but a quick one, you would find that some of the time the ring wants to go up, some of the time it wants to come down, and you go, well, how come it's going up then? Because it doesn't average out that way. The electrical currents that are generated in here don't just die and reverse when the fields here are switching back and forth. There's a delay, okay? There's a lag. Now, I want to show you a mechanical analog so that you can see that the driving forces are not always in line with the motion, okay? So let's take a look at this device over here. So what I have here is a mass hanging from a spring, and it has no net force on it. The spring is pulling up, gravity is pulling down, they're matched equally, there's no motion. Now I'm going to grab the mass and I'm going to pull it down like that. And right now the spring is pulling on it harder than gravity. But I'm helping gravity, so it's standing still. I'm going to let go of it, and let's watch the motion for a moment. Now what I want you to notice is where the maximum forces are. The maximum forces are either at the bottom when the spring is fully stretched, or at the top when the spring is kind of slacked and gravity is pulling down now. So the strongest forces are at the top or at the bottom, but notice where the highest velocity is. It's right in the middle when the forces are zero. So if you think of the forces as the magnetic field, or I'd say the magnetic field of the core as the driving force. and the electrical currents as the velocity, then you see how the two can be out of phase with each other. And when we add up, when you multiply the interactions, the forces, the Lorentz force in those different phases, what we find is that the forces upward are higher than the forces down. Now, the reason I made an issue of that is one of the motors we're going to talk about relies on that kind of like a delay, okay, an out of phaseness of the part that's moving. So far, all I've shown you is that these things behave like a linear motor, okay? How do we relate that to the rotation of a regular motor? How do we get there? Let's get this up here. We're going to go to another device. Whoops, sorry about that. And you may recall this was the transformer that we took apart. You could see all the pieces, the primary, secondary, and the core. Well, we're going to just use this as an electromagnet. We're just going to use the top coil to produce an alternating magnetic field. And this is going to help because what I'm going to try to do is create a magnetic field that goes across a space that we can put one of our little aluminum rings. Only instead of having it shoot up, I'm going to have it rotate. Like that, okay? All right, so let's turn this on. So that same effect can produce rotation besides just a linear motion. Well, let's look at another version of this. So this is a little longer cylinder, only what I've done is I've filled the inside with some foam and a dowel with a hole in it so that I can get it to rotate like that. We'll put this in here and let's energize the coil. Let me adjust this a little bit here, get us a little bit more oomph. Okay, so we not only have linear motion, we have rotation. So we're on the way to understanding how induction motor works. The first motor I'm going to introduce you to is a motor you probably have never interacted with and maybe never will because it is a three-phase induction motor, which is very common. Industry uses it everywhere. Big commercial buildings use it in their heating and cooling systems, elevators, pumps, fans. Very common, but not common in the home or small office building or in your everyday interactions. You are probably not dealing with three-phase power. But the three-phase induction motor is the easiest induction motor to understand. So we're going to start with that. Now, this probably looks very familiar. Yeah, it's that alternator we played with. And we converted the alternator into a synchronous motor. Remember that? All right. Let's review what happens when we put electricity into the stator of this alternator stator, which we're going to describe as an induction motor stator. So we've got the three windings, and they're all evenly staggered around. Now, if we power one of those windings, you recall we get a bunch of magnetic poles. If we feed alternating current into these three windings, then staggered in time and position, those magnetic poles appear to rotate. And of course, associated with those poles is a magnetic field within this space here. So we've got a rotating magnetic field. Let's do a little experiment. You remember this little guy here? We just spun him on that electromagnet. What I have here is this block of wood with these two legs, and there are strong magnets at the end. So this is free to spin, okay? And I'm going to put this on here. Let's scoot that out, all right? So when I spin this, I'm creating a rotating magnetic field, and look at how it pulls the aluminum around. It's not from any friction. That little black part that touches both, it's not moving at all. It's attached to this rod, which is attached to my handle. But as I spin that, I generate electrical currents in the aluminum, and those electrical currents want to go with the magnetic field. Now what we place in here is a rotor like this, which is very different than the synchronous motor. This had poles, either permanent magnets or an electromagnet in this case. This is a strange looking rotor. There's no commutator, there's no clear poles. How is it built? Well, it has layers and layers and layers of sheet steel. Those layers of steel have holes punched in them around the outside edge, and as we stack these together so it's nice and thick, we then pour molten aluminum or copper to fill in the holes, and then we have a mold that creates a ring on either side of this rotor. So now we've got these little rods of aluminum. Let me show you. Let me tilt this so you can see the three rods that should be visible here where I cut the ring away. There's three of them there, and they go all the way around. You can see these little aluminum dots along the outside. They're part of the a little bit exposed of the little rods that go all the way around. So rods connect from one ring to the other, so we have complete circuits in here, loops of aluminum. So as we have a changing, rotating magnetic field, it produces electrical currents in here, and those electrical currents interact with the rotating magnetic field, and they want to go with it. The forces are such that they pull the rotor around. It's really pretty straightforward, and that's how a three-phase induction motor works. You reverse the two of the terminals of the motor, and it'll spin the other way. Okay, so far so good. The thing is, you don't have three-phase power at home. You have a whole bunch of motors in your house that operate on single phase, but they're induction motors. So how do we make them work? Let's take a look at this diagram of a split capacitor motor. It's just a schematic. So we would provide the power here, a certain voltage, let's say 120 or 240 volts, and that would directly go to these two windings. This is really a two-pole motor, and so the power would go through these two windings, and we would produce a north and the south pole here. These two windings also would get that alternating current, but they have a capacitor in series with their circuit. Now, I won't go into how a capacitor works or how it's built in this session. What it does is it shifts the phase between these coils and these coils, so that, I mean, optimally and theoretically, we could get it to where when these are a maximum, these are a zero, and when these are a maximum, these go to zero. So that's what the capacitor creates, this difference in phase between the coils. Now, in an actual motor, there's an overlap between this coil and that coil and this coil and that coil. And the same here, okay? And the induction rotor part is the same as the one I described for the three-phase motor. Let's take a look at the two sine waves that would be feeding these coils when we have a capacitor in the circuit for one of them, okay? So here we have a split capacitor motor. There's the capacitor. And when I energize this, we'll see the two sine waves appear on the oscilloscope. And there they are. And you can see that the blue sine wave is starting here at maximum. As it goes, and the yellow sine wave is at zero. As the blue sine wave drops to zero, the yellow sine wave goes to maximum. As the yellow sine wave goes to zero, the blue sine wave goes to maximum. And then as the blue sine wave goes to zero, the yellow sine wave goes to maximum. Now, of course, here they're negative, and here they're positive. So that process continues throughout time as long as the motor is running. So you can see the offset in the timing of when they go to maximum. So let's apply what we just saw to a real motor. You can tell there's two windings here. Fortunately, they used a different color magnet wire for each of them. So there's a winding here and a winding here. Those two work together. Think of those as being the red windings that I just showed you on the diagram. And then these are the black windings here. And notice that they are overlapping. They're not completely separate. They are overlapping. Now let's apply what we saw on the oscilloscope to these coils. So we'll energize these two coils first, and let's assume that when they're energized, that this one becomes a north and this one becomes a south. Now, as they go down, as the sine wave goes through its time, the field goes to zero, but these go to maximum. Now, depending on how the two different phases are connected, this could become a north or that could become a north. Let's assume this one becomes a north, which means that'll be a south. So as this dies down, these go to maximum, and so it appears that there's a rotating magnetic field like that. Now, as these die down, these come back to maximum, but their maximums now are on the negative side of the sine wave. So they have reversed what they were before. This was a north. Now this is going to be the north, and this is going to be the south. And that process repeats around and around and around. This is a two-pole split capacitor motor. So we've got a rotating magnetic field. And the rotor is very similar to the the other one that I showed you. This one's almost easier to see the elements because the rods are very close to the surface and actually penetrate slightly through the steel laminations, and you can see the little lines that are attached to the rods that go from the outer ring to the inner ring, providing loops, pathways for the electricity to flow. It's just like this one. So let's put this in here. We've got a rotating magnetic field. Remember, it produces electrical currents in the rotor. Those electrical currents interact with that rotating magnetic field, and they pull it in the direction of rotation. Pop this in place, make sure it's free, and let's put this on here, and we turn it on. And we have a split capacitor motor. Split capacitor motors are in your heat pumps, air conditioners, your HVAC systems at home, your refrigerator compressor. This happened, the one I'm showing you here, happens to be out of a very nice air cleaner. Anytime you have these motors that run a long time, a split capacitor motor is a nice one to apply there. The toughest induction motor to explain is the split phase motor. This is the stator, the stationary part of a split phase motor. This is actually the motor that this rotor came out of that I've been using for some of the examples. You see how nice and tight the fit is. Just enough clearance so they don't touch. All right, this is a 4-pole motor. It would run at half the speed as that split capacitor motor, which was a 2-pole motor. This is the run winding here in gold. And if we energize this gold winding, the motor won't turn. First, let me talk about what happens. When we energize this, we're going to get a north and a north and a south and a south, and because it's alternating current, they're going to be switching back and forth. When we put the rotor in here, this run winding is changing back and forth, but the rotor will not spin because as let's say these are norths. When these go to here, the rotor does not have any kind of directionality to deal with. These two norths, let's say their half goes here and the other half goes here, and there is no clear direction. Same with the souths. There's no rotation occurring as far as the rotor is concerned. So in order to get this motor started, we have this second winding, a lot like the split capacitor motor. Now, sometimes we associate a capacitor with this. This particular motor, we didn't. Now, you know how a split capacitor motor works, so I will not start it with a capacitor so that we'll deal with a split phase motor in general. The windings in gold are different than the windings in green. These are thin wires, high resistance, but not as many turns, low inductance, high inductance. That difference creates a phase difference between when the magnetic fields go to maximum between these coils and these coils. What that means is, as these die down, these go to a higher level than they were, and then when they die down, these go to a higher level. Similar to what happened with a split capacitor, only the reason it's different is because of their inductive reactance. Remember the thing with the mass on the spring. When you've got, if I had a different mass on that spring, it would go at a different rate. I'm kind of oversimplifying this, but the important thing is the magnetic fields here occur at different times. In that case, then, we again repeat that process. If this is a north and this is a north, this is a south, and you can see the magnetic fields don't go across, they go kind of around as shown by the black arrows. This is a north, south, south. As these coils head towards zero because of the sine wave, these are out of phase with the gold coils. The green coils are out of phase with the gold coils. That means that as these go to zero, we're going to have, let's say, a north here and a north here. It could be the other way, depends on how we wire it, but let's assume that these are going to be the norths and these are going to be the souths. Then as these die down because of the sine wave, these now go to maximum again, but they're on the second half of the sine wave, so they are now at the negative side of the sine wave, so now these are going to be norths. They were souths originally, but now they're going to be north poles. So you see what's happening. We're getting a rotation, just like we were getting with the three-phase motor and the split capacitor motor. Now, when the rotor gets up to about 70% of its final speed, these types of motors turn off this winding. These wires are very thin. They would overheat if they ran for a long time. That's just the economics of this type of motor. We don't invest a lot in these wires. Okay, so this is spinning. But remember when we started, we said the rotor doesn't recognize a rotating magnetic field with this, because this is north-north, south-south, and then they reverse, but they could reverse in either direction, so the rotor can't tell which way it's going. But here's the way to think about this now. I'll do a little oversimplifying, but think of these as primaries of a transformer. And as they go from, say, a maximum north to a maximum south to a maximum north, they produce electrical currents in the rotor. Those electrical currents are out of phase with what's going on here. And this is rotating. So think of the rotor as sort of being instantaneously magnetized a certain way. When it gets to about here, these have now switched. They're behaving differently, and that existing magnetic field of the rotor is going to be pushed that way and pulled this way by this coil, and pushed that way over here and pulled this way by that part of the rotor's magnetic field. And the same thing happens at each of these intersections between the coils. It's sort of like a pumping process. These pump up that electrical flow, and as things switch, this ends up in a position for which the magnetic poles here push it around. And it just continues to spin like that, depending on which way the start windings started it. Now this motor is very common in your house as well. It is probably, I'm sure it's used for your garbage disposal. That's what this motor was. Your washing machine motor is typically a split phase motor. Your clothes dryer is a split phase motor. Look at some of these motors here in my shop. So this is a grinder and a tabletop drill press floor drill press. An old lathe, bandsaw, radial arm saw. Most of the noise you're hearing is from the equipment and not the motors. If you think that's noisy, remember what a commutator motor with gears sounds like. Okay. Well, we've got one final motor to take a look at. And it's called a shaded pole induction motor. These are the kind of motors that are like in your bathroom fans, or they're the little fan motors in a portable heater. They're very inefficient, but they're kind of rugged. They usually are very small, don't draw a lot of power. And let's take a look at how they're built. So here's two of them, and the reason I've got two of them is because I kind of modified one. This one, it's a two-pole motor. It's very common. And what makes them work is these little copper loops here on one corner of the pole, and there's another copper loop here on the corner of this other one, on the opposite corner here and here, diagonal, okay? Those little loops of copper act like a start winding, but they're not taken out. They're not turned off when the motor gets up to speed, and that's kind of what makes it inefficient. Those little loops waste some of the power. Let's take a look at this one here. We'll run it, and then now this one here is very similar. What I did though is I removed the little copper loops, and when you remove the copper loops, you kind of mess up its ability to start, and I wanted to show that to you. Now sometimes this one starts, but it is not the motor it used to be. If I stop it, it'll stay stopped. Okay? It's not spinning now. Now if I give it a little turn, it'll get going. Sometimes it'll even get up to speed. It should be spinning that fast if it could get going. Let's see if we got, whoops. So we need those little loops in there to make it start. This one here, if I stop it, it'll start on its own. And I'd like to show you something before we end this session. Now you remember this. When we energized the coil, we got rotation. The reason we got rotation is because of these little loops here on this piece of steel, this laminated steel. If I use this end, where these coils are too far away to affect, nothing's happening. I've got this all the way up, and it's not spinning. It's not until I use that side, and that's a little shading pole. That's what that is. And that creates that phase difference that allows this to rotate. Well, I hope you've enjoyed this session. I hope some of the information is useful for you. And thanks for coming, and I'll see you next time.